Script 1 was about the question, the 47-minute countdown clock, the history of failed attempts, the physics that makes this hard. The reason the tow sled architecture is the only version of this idea that obeys the laws of thermodynamics. The Phase 0 rad experiment, that would cost $150,000 and take 6 months and produce a binary answer. That was the argument for why this is worth doing. This script is about what happens if it works. Because the hollow fiber membrane contactor and the perfluorocarbon recirculation loop, the two core technologies at the center of this system, are not a single product. They are a platform. And the product line that grows out of a validated platform is considerably larger than a tow sled for military divers. I want to walk through that product line honestly. Not as a promotional exercise. As a technical assessment of what the same core hardware at different scales and different configurations actually enables. We will start with the sled itself, the first product, the one that validates everything. Then we will move to the other applications in sequence, from smallest to largest, from nearest to furthest. And I will be honest about which ones are near term and which ones require technology that does not yet exist. The discipline that made Script 1 worth watching is the same discipline that makes this one worth watching. We say what we know, we say what we don't know, and we say exactly how we would find out. Assume the Phase 0 rad experiment works. The metabolic loop closes. A living mammal breathes dissolved oxygen extracted from recirculating aerated seawater for 4 continuous hours without surface supply. What comes next is not human testing. What comes next is Phase 1, a full-scale tow sled prototype rated for pool testing, not ocean deployment. Here is what that prototype contains. The primary extraction module is a bank of commercial hollow fiber membrane contactors, the same Liqui-Cel X50 series modules used in industrial wine degassing and pharmaceutical-grade water treatment. Each module is a cylindrical housing roughly 50 centimeters long and 20 centimeters in diameter, containing approximately 1.4 square meters of hollow fiber membrane surface. At the water flow rates and extraction efficiencies we need, the Phase 1 sled carries 4 of these modules in parallel, housed in a rectangular aluminum manifold block with a single inlet and a single outlet. Seawater enters the manifold from the sled's intake scoop. It passes through all 4 modules simultaneously. Dissolved oxygen crosses the hydrophobic membrane wall into the perfluorocarbon fluid circulating on the shell side of each module. The seawater exits through a rear discharge port. The oxygen-depleted water does not recirculate. Fresh seawater flows through continuously. The PFC recirculation loop is a closed circuit. The oxygen-rich PFC fluid leaving the extraction modules flows to the degassing stage, a second, smaller membrane contactor running in reverse. On one side of the membrane, the oxygen-laden PFC fluid. On the other side, a partial vacuum drawn by a small brushless vacuum pump. The dissolved oxygen crosses the membrane from the liquid phase into the gas phase. The gas stream, now roughly 40 to 60% oxygen by partial pressure, flows into a 2-liter buffer reservoir made from carbon fiber-wrapped aluminum. The diver breathes from that buffer through a standard closed-circuit rebreather loop. Exhaled gas returns to a lithium hydroxide scrubber canister on the diver's back, where carbon dioxide is chemically absorbed. The scrubbed gas, now mostly the remaining oxygen and inert nitrogen, returns to the breathing circuit. The buffer reservoir is topped up continuously by the sled's extraction system running in real time. The pump is a brushless axial flow impeller, the same category used in electric outboard thrusters for kayaks and small inflatables. At the flow rates required, it draws between 180 and 350 watts depending on the diver's exertion level. The battery is a 2.4 kilowatt-hour lithium iron phosphate pack, the same chemistry used in marine trolling motors, housed in a sealed aluminum tube running the length of the sled's keel. At 350 watts continuous draw, That pack lasts approximately 6.8 hours. At rest state draw of 90 watts, it lasts over 26 hours. The Sled's outer shell is a rotationally molded polyethylene hull, the same manufacturing process used for kayaks and marine buoys. Neutral buoyancy is achieved by adjusting the volume of syntactic foam packed between the inner equipment frame and the outer hull. The entire assembly is 65 centimeters in diameter and 130 centimeters long, twabble on a 2-meter braided nylon umbilical that carries the breathing gas supply lines and a data cable for monitoring dissolved oxygen partial pressure in the diver's breathing circuit. Total estimated Phase 1 prototype cost, $1.4 million to $1.8 million, which places it squarely within the ONR SBIR Phase 2 funding range. Build time, approximately 14 months from contract award to first pool test. The Phase 1 test has one primary metric. Does the system maintain a safe oxygen partial pressure in the diver's breathing circuit between 0.16 and 1.6 bar partial pressure of oxygen continuously for a minimum of 4 hours at moderate swimming exertion, with no compressed gas supply connected? If yes, the project moves to Phase 2 ocean trials and the first production hardware contract. One of the less obvious implications of the tow sled architecture is what it does to the existing closed-circuit rebreather market. There are approximately 12,000 to 15,000 trained closed-circuit rebreather divers in the world. Military, technical diving, scientific research. Every one of them already owns a rebreather unit, a $10,000 to $25,000 device they maintain, certify, and trust their lives to. Every one of them is intimately familiar with the lithium hydroxide scrubber, the breathing loop, the oxygen partial pressure sensors. The tow sled does not replace any of that equipment. It interfaces with it. The connection point is the oxygen addition valve, a standard fitting present on every closed-circuit rebreather ever manufactured. In normal operation, that valve admits oxygen from a compressed cylinder strapped to the diver's back. The sled replaces the compressed cylinder with a continuous supply gas feed from the extraction system. The rebreather itself, the scrubber, the counterlung, the sensors, the heads-up display, operates exactly as designed. The diver's training and certification remain valid. The muscle memory for emergency procedures is unchanged. From the diver's operational perspective, the transition from tank-supplied to sled-supplied oxygen is a single equipment swap. Disconnect the compressed cylinder umbilical, connect the sled umbilical. The rebreather handles the rest. This matters commercially because it means the first version of this product is not sold to people who have never dived. It is sold as an upgrade to people who already own the downstream equipment, already have the training, and already understand the operational context. The market is small, technically sophisticated, and willing to pay for genuine capability improvement. Military procurement offices, technical diving outfitters, ocean research institutions. The initial unit price for the Phase 1 sled, before volume manufacturing economic supply, is in the range of $35,000 to $45,000. That is expensive. It is not prohibitively expensive for its target market. A single military diving operation that requires extended bottom time, 4, 6, 8 hours without surface supply, cannot be accomplished at any price with current technology. The sled makes it possible for the first time. The market for makes the impossible possible is not price-sensitive in the normal way. Version 2 of the product, after Phase 1 validation, after the production line is tooled, after the unit economics improve, comes in at a projected retail price of $14,500. At that price point, the market expands to serious technical divers, marine archaeology programs, offshore pipeline inspection contractors, and aquaculture facility operations. Version 3, the mass market entry, targets recreational rebreather divers at $4,299. That version requires additional engineering work on the sled size and weight, and it requires the PFC recirculation loop to be redesigned for lower maintenance intervals. It is a third-generation product, not a first-generation one. We name it here because the architecture enables it. We do not pretend it is imminent. The hollow fiber membrane contactor is not a novel technology. It has been in continuous industrial use for 30 years. What is novel in this system is the specific configuration, using a PFC intermediate carrier fluid to boost oxygen extraction efficiency from seawater and delivering the extracted gas to a breathing circuit. Strip out the breathing circuit. Keep the extraction module and the PFC loop. Now you have a device that pulls dissolved oxygen from a water column and concentrates it as a gas stream. That capability has applications that have nothing to do with human diving. The first is aquaculture aeration. Fish farms, whether pen-based ocean farms or land-based recirculating aquaculture systems, have a constant oxygen management problem. Fish at high stocking densities consume dissolved oxygen faster than passive surface diffusion replenishes it. The standard solution is electric aerators, devices that agitate the water surface or inject compressed air bubbles to increase dissolved oxygen concentration. They are energy intensive, they create acoustic disturbance that stresses fish, and they are inefficient. Most of the oxygen injected as bubbles escapes to the atmosphere before the fish can absorb it. A hollow fiber membrane system operating in reverse, injecting oxygen-enriched gas into the water column through the same membrane surface that extracts it in the diving configuration, is a highly efficient dissolved oxygen delivery system. The gas-liquid interface is enormous. Transfer is direct, no bubbles, no surface agitation, no acoustic disturbance. Oxygen utilization efficiency is 85 to 95% compared to 10 to 20% for conventional bubble aeration. The economics close quickly for salmon farming operations, which operate at stocking densities where dissolved oxygen management is a primary limiting factor on growth rate and survival. A modular membrane aeration system rated for a 500 metric ton annual production facility costs approximately $180,000 to install and reduces aeration energy consumption by an estimated 60 to 70%. Payback period at current electricity prices, under 3 years. The second industrial application is offshore infrastructure inspection. Offshore oil and gas platforms, submarine pipeline networks, wind farm cable arrays, and port infrastructure all require regular underwater inspection. Currently, that inspection is performed by either surface-supplied divers, limited to shallow depths and short exposures, or remotely operated vehicles, which cannot replicate the fine manipulation capability of a human diver for tasks like bolt torquing, seal replacement, and visual defect assessment. A diver equipped with the tow sled and rated for extended bottom time, 4 to 6 hours at working depth, can perform inspection and maintenance tasks that currently require either a saturation diving system costing $50,000 per day to operate, or a remotely operated vehicle that cannot perform the task at all. The addressable market for extended duration inspection diving in offshore energy infrastructure is estimated at $2.1 billion annually in North America and Europe combined. It is currently served almost entirely by saturation diving contractors. The tow sled does not replace saturation diving for very deep operations. Below 100 meters, the physiological nitrogen management problem is separate from the oxygen supply problem, and the sled does not solve it. But for the 30 to 80 meter depth range, where the majority of offshore inspection work occurs, the sled competes directly with saturation systems at a fraction of the mobilization cost. The third industrial application is underwater habitat life support. Small research stations, remotely operated monitoring buoys, and temporary work habitats for construction projects. These are discussed in the next segment because they connect directly to the question of scale. The core insight of this project, the one that separates it from every previous iteration of the artificial gill concept, is that the same membrane extraction technology scales across an enormous range of oxygen demand requirements. A single diver at exertion requires approximately 3 liters of oxygen per minute. A small 4-person research habitat requires approximately 15 to 20 liters per minute for life support, plus reserve capacity. A 20-person underwater workstation requires 80 to 100 liters per minute. A 100-person permanent habitat requires 400 to 500 liters per minute. In every case, the extraction hardware is the same. Hollow fiber membrane contactors, PFC recirculation loops, degassing modules, Buffer reservoirs. The hardware does not change architecturally as it scales, it multiplies. More modules in parallel, larger pumps, larger battery or grid-connected power supply. This is not true of compressed gas systems. Compressed gas systems require increasingly complex and dangerous high-pressure storage as they scale. A 100-person habitat running on compressed oxygen cylinders requires a gas farm that represents a catastrophic explosion risk, requires daily resupply logistics, and cannot be operated without continuous surface support. A membrane extraction system at that scale is a bank of industrial contactors running on grid power from a seabed cable or a tethered surface generator. It is not dangerous. It does not require daily resupply. It fails gracefully. A single module failure reduces capacity by a fraction of the total, and the system continues operating at reduced throughput while the failed module is replaced during a scheduled maintenance window. The first station-scale application is not a permanent habitat. It is a temporary hyperbaric work shelter, a pressurized bubble deployed at 30 to 50 meters depth for the duration of a construction or repair project. These shelters currently use surface-supplied compressed air from an umbilical. The umbilical is the limiting factor. It restricts the shelter's working range from the surface support vessel and represents a single-point failure mode. A self-contained membrane aeration system eliminates both constraints. The second station-scale application is a permanently deployed monitoring station, an unmanned or minimally manned platform on the seabed that supports oceanographic sensors, communication relay equipment, or environmental monitoring arrays. These stations currently require either battery replacement by ROV every few months or a power cable from shore. A membrane extraction system combined with a hydrogen fuel cell, using the extracted oxygen as the oxidant and seawater electrolysis for hydrogen, closes a fully autonomous power loop. The station generates its own power indefinitely from the seawater surrounding it. I want to be precise about what indefinitely means here. Seawater electrolysis for hydrogen production requires significant power input. The energy balance of a system that uses membrane-extracted oxygen to run a fuel cell that powers the electrolysis to produce the hydrogen that feeds the fuel cell is not a perpetual motion machine. It requires a net energy input from a tidal current generator, a temperature gradient harvester, or a surface-connected intermittent power source. What it does is decouple the station's oxygen supply from its compressed gas logistics chain and allow intermittent renewable energy sources to power continuous operations through the hydrogen buffer. That is a real capability. It is also a capability that requires engineering work beyond what the Phase 1 Sled prototype delivers. I name it here as a direction, not as an imminent product. The third station-scale application, and the one with the largest long-term potential, is a permanently inhabited undersea research station, analogous to a polar research base, housing 20 to 50 researchers for extended rotations. The Aquarius Reef Base, operated by NOAA off Key Largo for 30 years at 19 meters depth, demonstrated the scientific value of extended saturation habitation. It was decommissioned in 2012 due to operating costs, primarily the cost of maintaining compressed gas supplies and saturation diving support from the surface. A membrane-aerated habitat at equivalent depth eliminates the gas supply logistics problem. It does not eliminate all the other challenges of undersea habitation: thermal management, carbon dioxide scrubbing, structural integrity, communications, medical emergency evacuation. But it removes the most operationally constraining one. The project does not claim to build that station. The project claims to validate the oxygen supply technology that makes that station economically viable. There is a fifth application that does not come up in most discussions of this technology, and it is worth naming explicitly because it connects to one of the largest ongoing shifts in naval and oceanographic operations: autonomous underwater vehicles, AUVs and UUVs, the battery-powered robotic submarines now deployed for mine countermeasures, hydrographic survey, environmental monitoring, and submarine tracking, have a fundamental operational constraint. They are limited by their battery capacity. A typical military AUV has a range of 100 to 300 kilometers on a single charge. When the battery is depleted, the vehicle must surface and be recovered by a ship or dock at a fixed underwater charging station powered by a surface cable. Neither solution is tactically acceptable in a contested environment. A vehicle that must surface to recharge is a vehicle that can be detected and destroyed. A charging station tethered to a surface cable has a wire running to the surface that announces its presence. A membrane extraction system running on seawater, with no connection to the surface and no compressed gas supply, can power an electrochemical oxygen-hydrogen fuel cell that charges an AUV's battery pack at an underwater docking station. The docking station sits on the seabed or hovers at depth. It generates its power from the oxygen the membrane system extracts from the surrounding water. The AUV docks, charges, and departs. No surface contact. No logistics chain. No detectable umbilical. The technical requirements for this application are different from the diving application in one key way. The power density requirements are lower, but the operational duration requirements are much higher. A diver sled runs for 8 hours. An AUV recharging station needs to run for months or years unattended. That shifts the engineering challenge from battery life to membrane fouling management and long-term PFC fluid stability, both of which are addressable but require separate development work. The U.S. Navy's program for persistent forward-deployed AUV operations, the Manta Ray program and its successors, has specifically identified underwater recharging infrastructure as a critical capability gap. The membrane extraction platform described in this series is one of the few physically plausible solutions to that gap that does not require a surface connection. That is not an incidental overlap. It is a convergence point between the civilian diving product line and a defense application with substantial government funding behind it. We name it here because the architecture enables it. We do not claim it is the next product after the tow sled. We claim it is on the same roadmap, served by the same validated technology. I want to close the same way Script 1 closed, with the honest version of the argument. Here is what we know. Hollow fiber membrane contactors extract dissolved gas from liquids. They do this commercially, continuously, reliably, in food production and pharmaceutical manufacturing and power generation at industrial scale. This is not speculative. It is a 30-year-old technology with a mature supply chain. Perfluorocarbon fluids dissolve oxygen at 20 times the concentration of water. They are chemically inert, non-toxic, and approved for medical use in humans. The pharmacology and the fluid mechanics are validated. The combination of these two technologies, a PFC-assisted hollow fiber membrane contactor system, has been modeled and partially tested at small scale. The extraction efficiencies we need are within the range that published laboratory work suggests is achievable. The tow sled architecture, putting the pump, the battery, and the extraction modules in a towed housing rather than on the diver's back, is the design decision that makes the power and weight budget close. This is a systems engineering conclusion, not a materials science breakthrough. Here is what we don't know. We do not know that the integrated system, all components together, running continuously at human metabolic demand underwater, achieves the extraction rates that the component-level data suggests it should. Integration failures are real. Unexpected fouling of membrane surfaces by marine organisms. PFC fluid degradation over extended operational cycles. Pump cavitation at depth. These are the unknowns that the Phase 0 and Phase 1 experiments exist to find and solve. We do not know the actual service life of the membrane modules in a saltwater environment with continuous flow. Industrial Liqui-Cel modules are rated for multi-year service life in pharmaceutical water systems. Marine environments are more aggressive. Biofouling alone is a separate engineering problem that requires its own solution, probably an anti-fouling coating on the water-side membrane surface, possibly a periodic backflush cycle. We do not know the regulatory pathway for a life-critical breathing apparatus that uses an oxygen extraction mechanism that no existing certification framework was written to address. The FAA has rules for aircraft oxygen systems. The Navy has standards for submarine life support. NOAA has guidelines for saturation diving. None of them cover this. Navigating that regulatory space is a parallel workstream, not an afterthought. Here is what comes next. The Phase 0 benchtop experiment. $150,000, 6 months, 1 rat in a sealed chamber. Binary outcome. If it closes, Phase 1 pool-rated prototype sled, $1.4 to $1.8 million, 14 months, ONR SPY-R Phase 2 funding. If Phase 1 validates, first production contract for military diving applications, parallel development of the aquaculture aeration product line, first patent portfolio publication, first academic paper. If the aquaculture product validates commercially, self-funding development of the offshore inspection product. The habitat scale and station scale applications follow as the membrane module supply chain matures and costs decline. The long-term vision: permanent undersea habitats, autonomous seabed stations, ocean-scale environmental monitoring networks, is real. It is also 15 to 20 years from the Phase 0 experiment, and it depends on technologies beyond membrane extraction that are not yet mature. We name it because it is the true scale of what this technology enables. We do not pretend it is the deliverable of the first funding round, 1 rat. A sealed chamber, 6 months. That is the first card to turn over. Everything else follows from whether that card is a win. By C.J. Run at Whitstrom. Look, listen, or read in order to C.J. Run. C.J. Run, wire eternal Aqualung, your artificial gill, wire underwater tech, Navy diving, your hollow fiber membrane, PFC, wire perfluorocarbon, wire closed circuit rebreather, wire aquaculture, offshore inspection, wire underwater habitat, wire marine technology, wire SBIR, wire ONR, DARPA, deep tech, ocean tech.